Hello everyone. In this set of videos, I'm going to take a look at some issues that come when you are trying to finally build and productionize an embedded system, primarily involving Linux and FPGAs, as this course has been about, right? So in some sense, this is sort of trying to cap off everything that we have talked about over here. These are not topics that I'll be going into in a lot of detail, but they are important aspects that you need to be aware of as an engineer who might be building some of these systems. So they primarily revolve around the concepts of performance and production. Let's get into some of them in more detail. So the overall goals of what I'm trying to cover over here, to understand certain challenges that come up when we are trying to implement real-time systems and potential solutions. In particular, what happens when you try to use Linux for real-time systems. Power management is a very important aspect in most embedded systems. How do we deal with that? And what sort of support do we get from the Linux environment to help us to manage things. And when you finally want to build a product, there are a number of issues that come up in terms of security and the overall the chain of trust that you implement in terms of how you can guarantee that the code that you have written is what finally runs on the system, and a few aspects of that sort that also need to be considered. So let's start by looking at the problem of real-time performance, and what I mean over here is the real-time as defined in the context of embedded systems. Just to recap, right, because I assume that you're already familiar with the course on embedded programming, you would know that real-time does not necessarily mean fast. More important is deterministic, right? So for example, you're not necessarily talking about responses in the nanosecond time scales. You are, however, saying that if it is going to take milliseconds, you know exactly how many milliseconds it's going to take, or preferably microseconds. The point is, latency has to be bounded, has to be deterministic. That is probably more important than having something which is sometimes fast but can occasionally be extremely slow, right? And also there is this notion of determinism and how it impacts throughput, which we will look at briefly. So the first thing that we need to understand when we are talking about real-time systems is this notion of latency, and latency essentially refers to how long does it take for the system to respond to some event, right? Some occurrence, perhaps it was a network packet coming in to the card, perhaps it was somebody moving the mouse, perhaps it was some other kind of event, maybe a timer event or something else that occurred, and the system, well, the operating system, which is currently handling many different processes in the background, needs to respond to this, and the time that it takes in order to respond is basically what we call the latency. Now, normal Linux systems, as we use on desktops or laptops, is optimized for throughput, not exactly for determinism. Now, this is a little bit tricky to understand, right? So let's try and sort of look at where the differences even come from. What I mean by throughput is that we want the system to be fast. We want it to process things fast. Let's say that you're performing a number of calculations. You want to make sure that those calculations get done fast. At the same time, the process is also sort of jumping between, the processor and the operating system are jumping between many different tasks. Now, in the normal context, especially on something like a server, the primary thing that we are interested in is throughput. How fast am I able to perform a bunch of database search queries? How fast am I able to deliver a number of web pages that are being requested over the network? Determinism is something slightly different. What it says is, if an event happens, how quickly am I going to respond to it? Now, the interesting thing is that when you are dealing with interaction, for example, on a desktop, right, or on a laptop, the throughput may not be your primary consideration, because you are not always running like a heavy duty web server or a database server. On the other hand, you do want the system to very quickly respond when you move the mouse or you press a key, right? So interactive systems, especially laptops and desktops, tend to have a trade-off between the determinism and the throughput. So there are aspects of the Linux kernel that can be tuned for both sides. So before we get into that, the first thing to understand is what are the aspects that even affect these latencies. First of all, there is scheduling, right? And there is this thing called the process scheduler, I've already mentioned that the Linux kernel basically handles multiple different processes, right? There are tasks that are running in the background. So if I'm using a browser and let's say a PDF reader, and in the background there is some network connection going on, all of those are 3 different tasks. There would be others. In general, when an operating system starts up, there are tens, possibly hundreds of tasks that automatically get started in the background. And the operating system needs to keep switching between all of them, spends a certain time on each one of them, and then comes back to the next one. Right? So deciding which task to run next is decided by yet another task within the operating system, which is called the process scheduler. Right? So this is sort of the most important thing. It basically sits over there and wakes up once every so many milliseconds and decides, okay, what's the next task that needs to run. Now what happens over there is different tasks are given different priorities. In general, what you say is, if there is something interactive, let's say I need to move the mouse or I need to respond to a key press, that probably has to get a fairly high priority because the user needs to be able to see a response. Right? Now it could be that at the same time I have a task that is actually performing a long running query on a database, or it's trying to perform a large scientific computation. Right? Now how do I sort of stop that task and switch over to something else? That's where the term preemption comes in. I need to stop a particular task, probably not kill it, but at least like save its present state so that I can come back to it later, and then say I'm switching to something else. Right? So preemption is a good thing in an interactive or a multitasking system in general, but on the other hand, every preemption does incur a delay. So what happens is that the process scheduler now needs to deal with these preemption delays, right? And that adds latency to the scheduling. Now one of the bigger problems that happens is when you have locks. Now why would I need a lock? Let's say that I have 2 different processes that are trying to access the network card or a specific area in memory, or are trying to draw something on the screen. They need to decide which one gets access to that resource at any given point in time. That after all is almost entirely the purpose of the operating system, right? It allows multiple different tasks to access the same set of resources. So how does it do that? It uses locks. At any given point in time, the lock is given to one process. That process does whatever it needs to, maybe writing data into that resource or reading from the resource, and then it releases the lock, at which point the next task that is waiting on that particular resource can acquire the lock and then continue to process it. We saw this in the context of device drivers, right, where basically there were like certain kinds of critical sections where we would put a lock and say, okay, now let's say that I want to change the coefficients in a filter. I need to make sure that I lock it. The driver ensures that nobody else is reading or writing these particular coefficients at this point in time, change them, and then release the lock. Right? So locks are extensively used inside operating systems, but what happens over there is, now we have 2 things. We have tasks with different priorities, and we have locks that control access to resources. What happens if a low priority task ends up getting a lock on a particular resource? Right? What should the high priority task do? Should it wait, or should it just cut in there and say, wait, I need this resource, you need to stop using it right now. Okay, so there are a number of things, in other words, that ultimately require certain choices to be made, and which in turn adds to the latency of the system. All this ultimately means that there are certain unpredictable scheduling decisions that can make the scheduling latency unpredictable, and that is a bigger problem than saying that the latency is high. If the latency is bounded within certain limits, we are probably more willing to accept it than if it say that sometimes it's going to be extremely fast, but there are occasions when it can be arbitrarily slow. So scheduling is of course one part of it, which just happens when you have multiple tasks in the system, but it's not just tasks. You can also have interrupts. For example, I am doing certain tasks and suddenly somebody moves the mouse or presses a key or a network packet arrives. Each of those raises an interrupt. Right? Now, of course, we already looked at how IRQs are handled, and we have sort of got some rules of thumb on how to deal with them. One of them being that try and keep the IRQ handler part of it as short as possible. Right? And the idea is that we have certain critical sections where I need to make sure that I have captured the IRQ, I have recorded it, done something with it, but during that time I don't want another IRQ to come along and mess things up. I usually disable IRQs during that time. The good thing is most IRQs are level triggered, which means that even if I have disabled it for a while, if an IRQ does come, it will get handled, but later once I have sort of enabled IRQs again, right. So, but disabling IRQs in critical sections can in itself add to latencies, right, or make the latencies of responses to certain things unpredictable. High priority IRQs can block other IRQs. In general, there is also overhead associated with the interrupt controller, right. So, apart from this, there are a bunch of other things that happen in the Linux OS itself, right. Memory, as we have seen earlier, has a cache hierarchy, right. There is the L1 cache, which is like very fast, low latency access, but very small in size. L2 is slightly bigger, but higher latency. L3 is even bigger, even higher latency, and then the external DRAM usually can potentially have like thousands of cycles of latency, right, but can potentially have a high throughput. So, if you want to sort of bulk transfer and you have got the correct page activated, then yes, you can still transfer large amounts of data. The problem is that all of these things play into context switches, right. A context switch is when the processor is changing context from running one particular task to another task, right. The other thing that happens is whenever you have a DMA from a peripheral, that invalidates cache lines, it incurs other overheads associated with coherent access, or perhaps I have to explicitly perform a sync operation. Either way, that can also introduce new impact on the latency, right. All of this ultimately means unpredictable. So, you will see that this word unpredictable keeps coming up. That is part of the core Linux kernel, right. Normal Linux, as we understand it, is optimized for throughput. All of these things where we have these potentially unpredictable decisions over here are okay if they happen rarely, right, because most of the time it means that things work out fairly well and we get fairly good throughput on our system. The problem is real-time systems do not work that way, right, because this unpredictability, meaning that sometimes I can have extremely high latencies, is very often unacceptable for a real-time system. That is literally the definition of real-time. Okay. And yes, one more thing that comes into play is what are called page faults, right. We talked about virtual memory. Now, what happens with virtual memory? The whole idea of virtual memory is I have a virtual address associated with a given block of memory, and the point is that that particular block of memory may not exist in physical RAM at a given point in time. What the kernel usually does is, if you ask for 1 gigabyte of memory, it tells you, okay, use this set of virtual addresses, but it does not actually allocate 1 gigabyte of physical RAM for you at that point in time. Okay. What it does instead is, let us say you now go and access one block of memory over there. It says, okay, is this particular block already present in the physical RAM of the system? If so, go ahead and fetch it, everything is fine. But if not, it incurs something called a major page fault. That page of memory is not actually present in the physical RAM of the system. Now, is that a fatal error? No. What the operating system does is, it just sort of tells the process, or rather it just does not even tell the process, it just makes the process wait and says, let me sort this out. It goes and figures out a place in physical RAM where there is sufficient space for what you want, does the mapping in the translation look-aside buffer so that the virtual address that you are looking for now corresponds to this page in physical RAM, and at that point it says, okay, the page fault has been resolved and this process can now access this particular location in memory, right. So, this is essentially something called demand paging. When I ask for 1 gigabyte of memory, I am not actually getting 1 gigabyte of physical RAM immediately. What I am getting is a sort of promise saying that, yeah, you have 1 gigabyte, but well, promises can be broken, right. What if other processors have also asked for the same thing? You are sort of betting on the fact that not everybody is accessing 1 gigabyte of RAM at the same time. And what you could do further is something called swap, which basically says, okay, let us say there is one process which asked for 1 gigabyte of RAM, but it is not currently active. I will just push all its data out onto disk and give the memory that I have to another process that requires the RAM right now. Okay, so, there are many ways of sort of artificially giving the feeling that you have more RAM that you actually physically have, right. So, demand paging basically says, yes, a process might have asked for so much memory, but I know that they're not going to use all of it at once. So as and when they require access to a specific location in memory, I will actually allocate it and give it to them. Okay. So a series of what are called major faults and minor faults, I mean, these sound like there's something wrong with the system. It's not. This is just a regular part of the behavior of an operating system. These faults are used to trap out of the normal operation of the system, go perform a mapping, allocate the memory, allocate physical memory, perform the mapping of that virtual address to this physical address, and then get back to the process and say, yes, you asked for memory, here it is. Right? So the process doesn't even know that all this happened in the background. It's completely transparent. I run malloc, I access memories, and the operating system makes sure behind the scenes that things are working fine. Now, as you can imagine, let's say that you asked for a large amount of memory and suddenly the operating system realizes that it doesn't have that memory, it needs to go swap something else out, and then it needs to create free physical RAM, and then it needs to map it for you. That's a completely unpredictable latency associated with that. So all of these things that I have mentioned over here are sources of unpredictability. They are things that can give you non-deterministic latency impacts, right? Things where you can't say I'm guaranteed that the latency of responding to a particular event is going to be less than so many microseconds. Okay.